Hello. So in this video we are continuing our study of the Z transform, and we're going to look at some important, let's say, ways to get the inverse Z transform. Okay, so now one way to imagine or one way to understand the mechanics of the Z transform is by taking an LCCDE and understanding how the Z transform works. For example, let's say we have a discrete time system which has this kind of relationship. Okay, it has xn is equal to, yn is xn plus ayn minus 1. This looks like a recursive realization. So if you take the Z transform, we will write this as y of z, and this is x of z plus a times z inverse times y of z. Now you can take this y of z to the other side and you will get y of z multiplied by 1 minus a z inverse is equal to x of z. So your h of z, which is a transfer function defined as the ratio of the z transforms of the inputs and outputs, which is actually 1 by 1 minus a z inverse. Now notice that in this computation we are unable to figure out whether this the ROC is mod z greater than mod a or mod z less than mod a. So if you recall, in the previous example we were actually discussing outward sequence and inward sequence. The same question has to be answered here. Are you going to use yn to figure out, are you going to use yn minus 1 to figure out yn? In other words, we start with y0 and get y1, and then use y1 to get y2, and go y2 to get y3, and so on. If you're moving in the positive n direction, that automatically means that we are talking about an impulse response which is right-sided, and we will conclude that the ROC is mod z greater than mod a. However, the same LCCDE can also be written as yn minus 1 is equal to yn minus xn upon a. Now this will also have the exact same transfer function, but since we are using, if we imagine that we use y3 to find y2, and then y2 gives you y1 and y1 gives you y0, and we are going in the reverse direction, in that case automatically you know that you are going to have a left-sided impulse response. If you have a left-sided impulse response, the ROC automatically becomes mod z less than mod a. So that is something you have to figure out. Okay, this depends on the so just taking Z transform for a system doesn't give you the license to just plug in whatever ROC you want. The ROC is determined by the practical mechanics of the system. So now inverting Z transforms typically requires some bit of complex analysis, but in our course we are going to just look at some simple approaches. One is inspection. That is, you should look at the common table of Z transform which I have asked you to look at in textbooks, and if you do that, then you can say, if you see something like 1 by 1 minus half z inverse for mod z greater than half, you know that this satisfies the form of 1 by 1 plus a z inverse and has an outward ROC, so you can directly write 1 by 2 power n un. Or if you have something like let's say something like z inverse plus half z power minus 2, then automatically you know z inverse corresponds to delta n minus 1, z power minus 2 corresponds to delta n minus 2. So this is going to automatically give me delta n minus 1 plus half delta n minus 2. Now notice that I have been very I have actually been careless in not specifying the ROC, but for finite length sequences the ROC is always the whole z plane except possibly 0 or infinity, so I did not bother. So you can by inspection and by looking at the table you can obtain the inverse Z transform. The second approach is an extension of the previous. If you are given something like, let's say, if you're given something like a more complicated one, let's say we take a two-pole system, 1 by 1 minus 1/4 Z inverse and 1 minus 1/2 Z inverse, and mod Z is greater than half. Now this is an ideal candidate for a partial fraction expansion. So we can always write this as A by 1 minus Z inverse by 4 plus B by 1 minus Z inverse by 2, which is the same as A into 1 minus Z inverse by 2 plus B into 1 minus Z inverse by 4, okay, upon the same denominator. So we get the equating the terms, we get A plus B is equal to 1 and minus A by 2 minus B by 4 is equal to 0, which gives us the equation B is equal to minus 2A. So substituting that here, we get A is equal to minus 1 and B is equal to 2. So that automatically gives me, if you just now look, and mod Z greater than half means we go for the right sided sequence, which means if I substitute it over here, I get the answer as 2 times half power n, 1 by 2 power n un minus 1 by 4 power n un. Okay, so I use the partial fraction expansion to expand into, for a single pole, a combination of the addition of two single pole sequences, and for single pole sequences, 1 by 1 minus A Z inverse, you know exactly how to find out the inverse Z transform. Use that and then just give the answer. Be careful about the ROCs, okay? And then you can also use the if you are very if you like the series related approaches, you can use the power series. For example, 1 by 1 minus Z inverse mod Z greater than 1. Okay, so mod Z is greater than 1, which means that actually we have mod Z inverse is less than 1, which means that we can expand this as 1 plus Z inverse plus Z power minus 2 plus Z power minus 3 and so on, which clearly gives me the sequence delta n plus delta n minus 1 plus delta n minus 2 and so on, which you can easily recognize is un, right? So this power series is actually a very simple way to do it. You can also take something which is a little more non-trivial. Let's say we take log to the base e of 1 plus AZ inverse, and we have mod Z is greater than mod A. So mod Z is greater than mod A implies that mod AZ inverse is less than 1, and you know that the log admits a power series expansion. Of course, even for complex numbers it does. You can write this as AZ inverse. So remember, it's minus AZ inverse the whole square by 2 plus AZ inverse whole cube upon 3 and so on. And this corresponds to the sequence, and you can verify this. Basically, the sequence is defined only for n is equal to 1, 2, 3 and so on. So the sequence is minus 1 power n plus 1, because for odd numbers it is positive, for even numbers it is negative, and it takes the value a power n upon n for n is equal to 1, 2, 3 and so on, and 0 otherwise. So this is an interesting sequence, and you can use the power series. For this, the power series is probably the easiest approach, because by using other approaches will likely lead you to some complications. So these are some simple approaches to invert Z transforms. Notice that if you want to do some complex integration, you can do that, but typically for the purposes of this course, this approach is sufficient and actually powerful enough for you to handle a large class of signals. Thank you.